The right method catches problems early. The wrong one costs you time, yield, and sometimes the entire batch. As advanced processes like AI chips, CoWoS, and HPC rapidly progress, every critical step relies on high-precision surface topography measurement. The problem is, suitable analysis methods vary significantly across different samples. Are you really choosing the right one? Hey everyone, welcome back to iST channel. I'm your host today, Chaya. To receive the latest news and professional insights about the semiconductor industry, make sure to subscribe so you won't miss any of our videos. So, what is 3D surface topography measurement? Simply put, it captures a sample's surface height variations, roughness, curvature, and flatness. These geometric data help engineers determine whether the material or process is stable, detect abnormalities, and make timely adjustments. In the semiconductor industry, optical microscopes and contact profilometers have long been indispensable tools for surface inspection and basic metrology. However, as processes become more advanced, these tools may struggle to reveal microscopic details due to limited resolution. Contact-based probes also risk damaging fragile samples. Combined with manual focusing, which introduces potential human error and relatively slow measurement times, these methods can no longer keep pace with today's accelerated development cycles. As demands grow, more advanced tools are needed to overcome process bottlenecks. Today, we've invited iST expert Andy to help you choose the right methods and boost your efficiency.
Hi everyone, I'm Andy. Have you ever used one method to find a problem but got no results? Then switched to another and solved it immediately? It doesn't mean the first method was wrong, but it might not have been the right fit. In our lab, we often get asked which method works best for a given product. Today, I'll introduce 4 common surface metrology techniques to help you choose the one that fits your needs. First, let's look at the Surface 3D Profiler. It works based on the principle of optical fringe projection, casting light patterns onto the sample surface. Surface height variations distort the fringes, and by using the known incident angles, the system calculates the corresponding step heights, ultimately reconstructing the sample's complete 3D topography. We've noticed that most clients using 3D surface profilers come from artificial intelligence and automotive electronics module or packaging companies. For automotive electronics, reliability is critical because it directly impacts safety. Artificial intelligence products, on the other hand, aim to deliver high performance within limited space, which demands precision at every level. In short, when high performance and reliability are both required, every detail and structure must be precisely controlled. 3D profiling quickly captures height, area, and surface curvature of a sample. With edge detection software, it greatly reduces human error. It is especially effective for monitoring package warpage and solder ball consistency, helping lower the risk of poor solder joints. This image shows how we use the Surface 3D Profiler to check warpage in the BGA solder ball area. It quickly captures the contour of the solder ball surface, calculates the height of each ball, and evaluates overall coplanarity. This makes it easy to assess the consistency across the entire component. The Surface 3D Profiler also supports high reflective, low reflective, and even transparent samples, which makes it especially suitable for advanced packaging like CoWoS. Since it uses a non-contact measurement method, there is no risk of damaging the sample. The Surface 3D Profiler offers Z-axis resolution between plus or minus 2.5 and 4.0 microns, making it ideal for scanning large area samples. It works well for components and PCBs within 30 by 15 centimeters. For samples larger than that, multiple scans are required and the stitch results may not be as accurate as a single full scan. The second method is the white light interferometer. It also relies on optical principles, but the approach is quite different from the Surface 3D Profiler. In simple terms, it projects light onto the sample, and the surface height variations create changes in the reflected interference fringes. These changes are then analyzed to reconstruct a nanometer scale 3D topography and calculate surface roughness. The white light interferometer is also a non-contact measurement method, with Z-axis resolution down to around 1 nanometer. This image shows the surface roughness of a metal sample after acid cleaning. The measurement covers an area roughly 300 microns across, and the average roughness is over 1 micron. The white light interferometer is mostly used for measuring the surface topography of opaque materials like metals, circuit patterns, and plastics. It doesn't work well on transparent materials such as glass. Next, we have the atomic force microscope. It uses a silicon probe with a nanoscale curvature radius to scan the surface and capture height variations. IFM can operate in both contact and non-contact modes. Its biggest strength is its exceptional z-axis resolution, which can be less than 0.1 nanometers. This image shows an IFM scan of photoresist, specifically the polymer material polyamide, which is commonly used in semiconductor processes. It captures a 2-micron by 2-micron surface area, with an average roughness of just around 8 nanometers. IFM is also well suited for extremely flat surfaces. It can be used to check whether a wafer or glass surface is truly clean after cleaning processes. It also helps evaluate the uniformity of thin films after coating. And by monitoring surface roughness before and after etching, it helps prevent reliability issues caused by delamination in later stages. Finally, let's take a look at Shadow Moiré. Its principle is similar to the Surface 3D Profiler. Pattern fringes are projected onto the sample surface, and the interference created between the light and the surface reveals height variations. In recent years, with the rise of heterogeneous integration and 3D packaging, different materials are often joined together through high-temperature processes. But due to differences in their coefficients of thermal expansion, thermal stress can easily build up at the interfaces, affecting the final bonding quality. That's where Shadow Moiré comes in. In this image, you can see how a 3D overlay of IC and PCB surface data helps visualize overall shape matching. The color-coded height map clearly highlights areas of misalignment or warpage, making it easy to spot issues at a glance. Shadow Moiré offers a z-axis resolution of about 2.5 microns, similar to the Surface 3D Profiler. It's well suited for large area samples like CoWoS packages or PCBs. In our lab, we use Shadow Moiré to help IC design houses, foundries, and OSATs simulate warpage data in advance. That way, they can fine-tune stencil designs and reflow profiles to reduce the risk of open or short failures caused by warpage during the SMT process.
Based on the advanced surface metrology techniques Andy just shared, we recommend selecting the right tool based on your specific needs. You can choose a single method, or combine multiple approaches to get more complete data. Each technique has its own strengths and limitations. For example, AFM offers extremely high precision but has a limited measurement area, while Shadow Moiré covers large areas but with lower resolution. For complex structures like CoWoS and fan-out, where both integration and precision are critical, combining techniques is especially effective. You might pair white light interferometer with AFM, or use the Surface 3D Profiler together with Shadow Moiré. This gives you both large area coverage and fine detail resolution for a more complete picture. We hope today's sharing helps you quickly find the surface metrology method that best suits your needs and improves both development efficiency and product yield. We've also prepared a comparison table of advanced measurement tools. Feel free to click the link in the comments to request a copy. For more detailed content, you can also check out the full Tech Classroom article linked below. That's a wrap for today. Bye-bye. If you enjoyed our video, don't forget to like, subscribe, and hit the notification bell so you won't miss any updates.